we'll just see what happens. So last time I had these things about these phase portraits of the linear systems. So I read a little more in the textbook, and then I understood a lot better what was being said and was not being said. So then I wanted to clarify, because I was like, oh, didn't I realize this last time? So let me try to bring this from the beginning one more time. Also, I was thinking about this last night, how fascinating this concept of looking at the small ones is, the small 2x2 systems, because there's so many things in nonlinear systems where I'm like, I want to fix that. This seems like too hard or whatever. And then I was like, well, how would you? And I was like, oh, start with the 2x2. So here we were. So let me review where this was at. So the phase, I know this seems like it's not related to anything, like this is not even about nonlinear systems, but what I learned from this was something where I was like, oh, that's right, I have to tell everyone to be careful with your math proofs. So, because I thought this was good, because I realized that I was making assumptions that I like, okay, phase portraits of linear systems. When I started writing it out the other day, or last night, I was writing out, like, I was like, oh, I found that part in the book that tells why this is true. As I started writing it out, like, word for word, copying it onto here so that I could tell you today, then I was like, wait a minute, that doesn't say exactly what I thought it said. I was being non-rigorous and making assumptions where I was going from one thought to another thought, but without the middle thoughts. And I was like, oh, this is actually a good point where I need to bring this up and say, make sure you don't do what I just did, like on paper. So we were looking at, what the point here was to say, like, okay, if you have x dot equals ax, a has some eigenvalues, lambda 1, lambda 2, which may be equal and real. They could be complex. They could be non-equal and real, etc. If they're complex, they're clearly not equal, because they would be complex conjugates if they were. They're not equal then. So we were looking at systems of this type, x1 dot equals a11 x1 plus a12 x2, and x2 dot equals a21 x1 plus a22 x2, and then x sub 0 is x0. So we were looking at these. So this was very specifically a 2x2 system in terms of that A is a 2x2 matrix. We said that, okay, given these eigenvalues, these are the eigenvalues of A, that you can find an M. Whoa. You can find an M such that if you set x equals mz, then you can find an invertible M. Then z, so I guess this is part of the point of, this was not the point, but let me just make sure I make this note. Whenever you're doing proofs, you want to make sure that everything you're doing is actually possible. So here, if I just said you can find an M such that, like, z equals M inverse X, for example. Now that's only possible if M is actually invertible. So it was very important that I add this word invertible here. And so this is just something that you'll pick up over time about all the details of, like, whenever you do a proof, you have to be, like, really rigorous to go step by step and to say, like, okay, can I get to this step from the prior step? And are there any additional conditions that are necessary for that to happen? And then, I don't know if you've ever done this before. You've never done proofs like these before, right? Yeah, it takes some getting used to get into the mindset of, like, all these details. So x dot equals m z dot, or z dot equals m inverse x dot, which if you plug in what x dot is here, then you get z dot equals m, I think this should say x dot equals m z dot. Z dot equals m inverse x dot. Z dot equals M inverse, and then X dot is MZ dot, or AX equals M inverse A MZ?
Yes.
Okay. So then it's possible, essentially what this is saying is, for this 2x2 linear system, and even for systems bigger than that, you can find an invertible M such that you can transform the system so that there's a Z, there's these new, that each vector X, I guess, is being mapped to vector Z, and then you get this new thing. And then in this new matrix, what it is that the M inverse AM can take one of three different forms based on, three different forms with respect to the eigenvalues of the original A. So either it can be lambda 1, 0, 0, lambda 2. This is with the eigenvalues of the original A matrix. These lambda 1, lambda 2 are real, but not necessarily distinct. The other form you can get is lambda 1, 0, lambda. That is another form that you can get. Is any of these pens working? And then, so here, lambda 1 equals, yes, this one is, equals lambda is real. And then the last case is, so these are all the cases that can happen for a 2x2. Of course, if it's bigger, then you can have more cases because there's more like permutations you can make of the entries because there's more than 4. And so this is where lambda 1 is equal to alpha plus j beta, and lambda 2 is alpha minus j beta, or b. So then we went through, and what we said last time and the time before that was we said, okay, this is great. We can actually go back to then the z coordinates and say like, oh, okay, so I could plug in each of these types. So I could say, oh, okay, pretend that z dot equals lambda 1, 0, 0, lambda 2. And then here have like z1, z2. You can then write out what the differential equations are of this system, because now it's, this is just a system that's being written out here. You could solve them by hand because it's only a 2x2. You'd find solutions. Then you could start plotting them. And we said that, okay, so for these many different cases, we have several different major sorts of phenomena that might be observed. We expect certain things like either this kind of implies the eigenvalues are not equal in this case. This would be like lambda 2 is less than lambda 1 is less than 0, z1, z2. You can see these by just plotting these solutions. And then there's all these other kinds. You could have the ones that are like this. You can have the saddle points where they go something like that maybe. There are many different cases, and they're all about the eigenvalues of the original A matrix. It's all about the eigenvalues. It's all about the eigenvalues. Of A, which happen to be the same as the eigenvalues of this M inverse AM, because like the eigenvalues of this matrix are clearly lambda 1 and lambda 2 also, and stuff like that. So, okay, so then this is the part where last time I started, I think, kind of messing up and being not fully rigorous. So we've agreed to this point what's going on. So then we started saying like, okay, what I really wanted to know was what's going on about the x1 dot equals f1 of x1, x2. So still we have a 2 by 2, but now it's nonlinear. And we started saying like, okay, I could make the linearization of this so very close to the origin. Maybe I could say through Taylor series, this is approximately true. This is what we usually do in like a, before we get to nonlinear systems theory, everyone always linearized. In your classes. And then, so this is sort of the second nature to say like, oh, okay, what can I do with the linearization? So I know what happens for the linear systems. I know that in the neighborhood of, I guess that's 2, 2, correct. Thank you. I know that in the neighborhood of an equilibrium that I can try to approximate the behavior with, or that a Taylor series should be a good representation of the system. Oftentimes we say that we can approximate that with, or that we will try to approximate that with a linearization around the at the equilibrium point, and then just neglect higher order terms. A lot of times we just do that. And it makes sense if the system, so under what conditions does neglecting higher order terms kind of make sense? That would be things like if x dot is equal to x plus x squared. We know that if we get to very infinitesimally close to the equilibrium of 0, that this, say that we're at like 10 to the negative 10 here, plus 10 to the negative 10 squared, clearly this is negligible compared to that number. So it makes sense that if you have linear terms, it makes sense that they could be, I guess a word you could say is it's dominating in some sense, in that near the origin, when you plug in a number into the linear term, it's way bigger than you plug in the number into the nonlinear term. So there's the idea about the linearization dominating. So there are many cases that it makes intuitive sense to say like, okay, maybe I will try to approximate with like that. I'll try to approximate like that. So then where we were kind of leaving off last time was to say, okay, great. So there's some relationship then between the linearization and these face portraits. And I just sort of threw them on the board last time and said like, this has something to do about perturbations around the equilibrium. But I was not rigorous, and therefore I made some statements that I believe are incorrect. So let's look at this in more detail. So it turns out that as much as I thought, so last time, let me just clarify what I said last time and then what is actually more true. Last time I said, oh, if you think about the like perturbations for the linear system, then think of the nonlinear system like a perturbation. Therefore, if the eigenvalues would change with a perturbation, then that means that's how we got the nonlinear result. Okay, well, what I thought about last night when I was reading the textbook, I was like, wow, that was really hand-wavy. That skipped like 20 steps. And I don't, like, that is not the way to do proofs at all. So then I was like, all right, let me revise this. Let me go through what it does say and what it doesn't say. There's gaps. I don't think the textbook actually fully fills the gaps, and I don't necessarily know. Of course, we could go look, but I think that this is a good exercise in realizing partly like how detailed you have to be in looking at stuff, and also what things to look for what things say and not what your mind just wants to jump to a conclusion, and then also to recognize that there's a lot of literature out there that's not covered in this textbook on things where, like, because I think then this is also a good skill for reading nonlinear systems papers, that there's going to be a lot of times people will say, based on the theory from such and such thing, here's what holds. When you read that paper, you don't know that theory. You could go look it up, and there's definitely value in doing that. Like if you can prove it yourself, if you can follow their proof and prove it to yourself, then you can feel confident.